Imagine trying to find one specific person out of the entire population of a city like Houston or Madrid. That's a monumental task, right? Well, scientists at Oxford University have just accomplished something even more incredible, but on a microscopic scale. They've managed to create a quantum bit, a qubit, with a staggering level of precision. The chances of achieving this specific stable state were just 1 in 6.7 million. This isn't just a small step forward, it's a giant leap in the quest to build a truly powerful quantum computer. It's like finding a single, perfectly flawless grain of sand on a vast beach, and it could be the key that unlocks a new era of technology. This breakthrough is so exciting because the biggest challenge in quantum computing isn't just about making qubits, but about making qubits. For years, the fundamental building blocks of quantum computers have been frustratingly fragile and prone to errors. They are like trying to build a skyscraper out of soap bubbles. The slightest disturbance can cause the whole thing to collapse. The Oxford team, however, has found a way to make their soap bubbles significantly stronger. This incredible fidelity, this 1 in 6.7 million success, means we are getting closer to a world where quantum computers can solve problems that are currently impossible for even the most powerful supercomputers we have today. This number, 6.7 million, represents the purity and stability the team achieved. Think of it like tuning a radio. Most quantum systems are filled with static, making it hard to hear the music. You might get bits of unprecedented clarity. This level of control is the holy grail for quantum engineers. It's the difference between a fuzzy, unreliable signal and a crystal clear broadcast. It means that the dream of a large-scale, fault-tolerant quantum computer is moving from the realm of science fiction into the world of tangible engineering. Before, useful quantum machines seemed like a distant goal, perhaps decades away. But with a building block this reliable, the timeline could shrink dramatically. This achievement isn't just a new record to be celebrated in a lab, it's a foundational piece of the puzzle. It tells the global scientific community that the path forward, while still difficult, is clearer than ever before. This single, rare success could be the spark that ignites a revolution in computing. Beyond zeros and ones. To truly appreciate what the Oxford team has done, we need to understand what a qubit is. Your phone, your laptop, every digital device you own runs on classical bits. A bit is the simplest form of information possible. It can either be a 0 or a 1. It's like a light switch which can only be on or off. Simple, reliable, and the foundation of all modern computing. This binary system is powerful, but it's limited. It can only process information one step at a time, in a straight line. For certain massive problems, this step-by-step approach is like trying to empty the ocean with a teaspoon. It's just too slow. Now let's enter the weird world of quantum mechanics. A qubit, or quantum bit, is the quantum equivalent of a classical bit, but with a superpower. Thanks to a principle called superposition, a qubit can be a 0, a 1, or, imagine that light switch again. A qubit isn't just on or off, it's like a dimmer switch that can be at any position in between, and in a sense, all positions at once until you look at it. This ability to exist in multiple states simultaneously is what gives quantum computers their incredible potential. It allows them to explore a vast number of possibilities all at the same time. This both-at-once capability is where the magic happens. If you have two classical bits, you can represent one of 4 possible combinations, 00011011, at any given moment. But with 2 qubits, you can represent all 4 of those combinations simultaneously. As you add more qubits, this power grows exponentially. With just 300 qubits working together, a quantum computer could process more possible values than there are atoms in the known universe. This is why quantum computers aren't just slightly faster versions of what we have now. They are a completely different kind of machine, designed to solve a different class of problems. So why does this matter? Because many of the world's most complex and important challenges are too big for classical computers. Things like designing new life-saving drugs, creating new materials with incredible properties, or breaking sophisticated encryption codes involve a mind-boggling number of variables. A classical computer would have to check each possibility one by one, which could take millions of years. A quantum computer, by exploring all possibilities at once, could find the solution in a matter of hours or days. Qubits are the key to unlocking this immense computational power and tackling the problems that have stumped humanity for generations. So if qubits are so powerful, why don't we all have quantum laptops? Well, The main reason is a problem called decoherence. Qubits are honestly just incredibly sensitive. The slightest vibration, a stray magnetic field, or even a tiny change in temperature can disturb their delicate quantum state and cause them to decohere or lose their information. This is what makes them so error-prone. Now, the 1 in 6.7 million figure from Oxford is a measure of how well they've protected their qubit from this noise. It means their qubit performs its calculation correctly with a fidelity of 99.999985%, an astonishingly low error rate. The Oxford team achieved this by creating a quantum quiet room for their qubit. They used a specific type of qubit, a trapped ion qubit, where a single electrically charged atom is held almost perfectly still by electromagnetic fields inside a vacuum. By refining their control over these fields and shielding the ion from external disturbances with incredible precision, they effectively silenced the quantum static that causes errors. This level of control is like a world-class surgeon performing a delicate operation in a perfectly sterile, silent, and stable operating theater. It allows the qubit to maintain its quantum state for longer, giving it more time to perform useful calculations. This extreme reliability is crucial for building a real, working quantum computer. Imagine trying to write a novel on a keyboard where every few hundred keystrokes, a random letter appears. You'd spend more time correcting errors than actually writing. Early quantum computers are like that. They make so many errors that the results are often useless. To overcome this, scientists need to build fault-tolerant systems, which use multiple physical qubits to create one more stable logical qubit. The higher the fidelity of the physical qubits, the fewer you need to build a reliable logical qubit, making the whole computer much more efficient and feasible to construct. What Oxford's breakthrough shows is that achieving near-perfect physical qubits is possible. Before this, many thought that the error rates of individual qubits would always be too high, forcing us to build impossibly large machines with billions of qubits just to correct for all the mistakes. But by proving that a single qubit can be controlled with such incredible accuracy, the Oxford team has shown a more direct path forward. It suggests that future quantum computers might not need to be as monstrously complex as we once feared. Their work provides a blueprint for quality over quantity, a vital step in the race to build a machine that can change the world. The work at Oxford isn't happening in a vacuum. There is a global race to build the first truly powerful quantum computer, with major players from both academia and the tech industry pushing the boundaries of what's possible. Tech giants like Google, IBM, and Microsoft are investing billions of dollars into their own quantum research labs. Each is exploring different physical systems to build their qubits. Google and IBM focus on superconducting circuits, which are like tiny, supercooled artificial atoms, while Oxford and others champion trapped ions. This competition is fierce, but it's also incredibly productive, as each new discovery helps the entire field move forward. The potential applications of this technology are what drive this intense competition. In medicine, quantum computers could simulate molecules with perfect accuracy, allowing us to design new drugs and treatments for diseases like Alzheimer's or cancer in a fraction of the time it takes today. In finance, they could optimize investment strategies and model economic systems with unprecedented detail. For science, they could help us create new materials, like room temperature superconductors that would enable lossless energy transmission, or better catalysts to combat climate change by capturing carbon from the atmosphere. Of course, with great power comes great risk. One of the most talked about applications of quantum computing is its ability to break many of the encryption methods that protect our digital information today. The security that underpins online banking, government communications, and private data could one day be shattered by a powerful quantum computer. This is why researchers are also working on quantum-resistant cryptography, new forms of security designed to withstand attacks from both classical and quantum machines. The race to build a quantum computer is also a race to protect ourselves from it. Ultimately, this news from Oxford matters because it signals that this transformative future is getting closer. The development of a nearly perfect qubit is not just an academic curiosity, it is a critical milestone on the road to a new technological age. While we may still be years away from having a quantum computer on our desks, the foundational breakthroughs are happening right now. The progress being made today will shape the world of tomorrow in ways we are only just beginning to imagine. So the real question isn't just if this technology will change our world, but how will we choose to use it when it does?